Section 5.4 has three main things that we want to do. Indefinite integrals, so that's really just introducing notation for the general antiderivative. We're going to practice some more challenging antiderivatives where we have to manipulate them with algebra some first, and the net change theorem. So let's get going. So since both parts of the fundamental theorem of calculus establish the fact that integrals and derivatives undo one another, it makes sense to use an integral to represent the antiderivative. So there is the official definition. The integral of f of x equals capital F of x means that capital F primed is lowercase f of x. Now keep in mind that indefinite integrals have answers that are families of functions. You always have to add c. So there's infinitely many solutions to an indefinite integral. A definite integral has a definite solution. It has one answer. Okay, there's just a quick example. Secant squared, the integral is equal to tangent x plus c, because the derivative of tangent of x plus any constant is equal to secant squared. Here's a table of indefinite integrals. You should have those all stuck in your brain like glue. There is a Quizlet that you can use to practice them. Now we adopt the convention that the general indefinite integral antiderivative is only valid where it's valid. So we don't have to divide it up into pieces if there are holes in the domain, like the integral of 1 over x squared is obviously not defined when x is equal to 0. So let's look at an example that doesn't just jump right out at you and tell you what the antiderivative is. We have the integral of cosine of theta divided by sine squared of theta. So, usually when we see trig functions, we simplify them, but this time we are going to rewrite it using some of the ratio functions. The fact that we can separate this into cosine of theta over sine of theta times 1 over the sine of theta. Cosine over sine is cotangent. 1 over sine is cosecant. We always have two cosecants and a cotangent, so the antiderivative of this is negative cosecant of theta. Don't forget to add c. Easy enough. There's the pretty answer. Let's practice a couple more. Number 6 here. Not really that complicated. You just have to rewrite it with a rational exponent. So the 5 goes on top, the 4 goes on the bottom. Index always goes on the bottom. And then it's just a simple add 1 to the exponent, divide by the new exponent. So x over 5 over 4 plus 4 over 4 is 9 over 4. And just because I can, I'll bring the 4 up top, leave the 9 down below, and add c. I would give you full credit if you left it like that. That's fine. Let's see, number 15. The integral of 2 plus tangent squared of theta. So first thing you think, well, is tangent squared the derivative of something? It's not. Secant squared, however, is the derivative of tangent. And if we think about Pythagoras, we can rewrite tangent squared as secant squared plus or minus 1. If you've forgotten that, remember you can always get the Pythagorean identities back. Sine squared plus cosine squared is equal to 1. Tangent sine over cosine, so divide everybody by cosine. So sine over cosine is tangent. Cosine over cosine is 1. 1 over cosine is secant. So I can replace this. 2 is 1 plus 1, so 1 plus 1 plus tangent squared of theta. Come down here. I'll replace 1 plus tangent squared with 1. So I replaced this whole thing inside the set of parentheses with secant squared, and I still had that 1 left out in front. So this is theta plus the tangent of theta plus a constant. Pythagorean identities, I do expect you to have memorized Pythagorean. Now, number 18. One of the easiest trig identities to remember is sine of 2x. I don't know all of the trig identities, but that one I do have memorized. Sine of 2x is equal to 2 sine x cosine x. And I expect you to memorize that one. Now I can cancel. So I just have 2 times the cosine of x. And the antiderivative of cosine is sine. Always add c. Easy enough. And now we can do a little more complicated ones with definite integrals. Notice all of these answers we've had. A family of functions. You could add 1, you could add 2, you could add 11, you could add 13. You could add 1,000,000, you could subtract 1,000,000, and you get as many different answers as you want. With a definite integral like number 5, example 5, you're going to get a definite answer. The integral from 1 to 9, and I'm going to go ahead and divide it into pieces. So I have 2t squared over t squared plus t squared times the square root of t over t squared minus 1 over t squared. Now I'll simplify stuff. Go away, go away. Still going from 1 to 9, but I have 2 plus square root of t is the same as t to the 1/2 power minus t to the minus 2 power. Now I'm modeling what I want to see on your test paper. I want to see the integral written down. I want to see the antiderivative written down. So 2t, add 1 to the exponent, divide by the new exponent, add 1 to the exponent, divide by the new exponent. And then we put our vertical bar that says to evaluate it from 1 to 9. So I plug 9 in first. 2 times 9. I'm going to go ahead and bring the 2 up top. I have 9 to the 3 halves divided by 3. I have minus minus, so plus 1 over 9. Then I subtract off what I get when I plug 1 in. 2 times 1 plus 2 times 1 to the 3 halves, which is just 1, divided by 3, plus 1 over 1, which is 1. Okay, let's combine stuff. We have 18. I have 9 to the 3 halves, which is the square root of 9, which is 3 cubed. 27 divided by 3 is 9, plus a ninth. I have minus 2 plus 1. Yep, everything in there is positive. So minus 3 minus 2/3. And then when you do all the arithmetic, I'll pause for a minute and do it. Okay, I didn't do it. I looked at the answer right there. It's 292 over 9. Now, your calculator does have a button that calculates definite integrals. So let's take a look at it and see what we get. Press on, of course, and then we'll clear out the old stuff. Press second, E to the button. That gives you the definite integral. We are going from 1 to 9. And I'm going to write it just the way it is. I'm not going to even simplify it. So I'm going to open up a set of parentheses for my numerator. 2x squared plus x squared, second square root of x, arrow over to get out from underneath the radical, minus 1. Close that set of parentheses on top of x squared. Now you have to use x because it already has the differential for x in your calculator. And it has a little hourglass sitting up there that tells you it's working on it. But on your test paper, I would want to see the antiderivative. So here's the antiderivative. I want to see that you know to plug the top number in first and the bottom number in second. And then you can let your calculator do the heavy lifting, and eventually it's going to come up with an answer. Now, if you have trig functions, you may not get an exact answer. Well, we did get an exact answer on this one, but we don't always get an exact answer, especially if it would be an answer with a pi or a square root in it. It would give you a decimal answer. So the best you can do is check your answers. Don't count on this to do your work for you. So let's look at some practice problems. I'm actually going to let you do that first one on your own. I want you to distribute that t through the parentheses because we do not have a product rule for integrals. I'm going to pause and we'll compare it. Okay, I FOILed, I distributed, I ended up with a trinomial that's easy to use the power rule. Add 1, divide by the new exponent, add, divide. I plugged my 1's in and I got an answer. I also went ahead and plugged it into the calculator and checked my answer. I made it into a fraction so I could see that, yes, indeedy, I had it right. So let's look at the next one. And this is number 30. This time we're integrating with respect to p, but it doesn't really matter. You can integrate with respect to whatever variable you want to. This one you need to recognize. What is the antiderivative of 1 over 1 plus p squared? Because I can pull that 4 out of in front and just attach it to the answer. It's the inverse trig function and its inverse tangent. You need to get those memorized. So inverse tangent of 1 minus inverse or arctangent of 0. So what is the arctangent of 1? Well, the thing whose tangent is equal to 1 is where cosine and sine are the same, which is at pi over 4. And inverse tangent of 0 is 0. So my answer here is pi. Easy peasy. I think I'll let you do number 34 and then we'll compare answers. So I'm going to go ahead and pause. Okay, first part was easy. Add 1 to the exponent, divide by the new exponent. Remember when we took the derivative of 5 to the x, we would multiply by the natural log of 5. When we take the antiderivative of 5 to the x, we divide by the natural log of 5. And then we evaluate it from 0 to 1, plug 1 in, plug 0 in, 5 to the 0 is equal to 1, combine like terms, and you're done. You could plug it into your calculator, but you will not get an answer that looks like that. So if this were a WebAssign problem, you would most definitely need to do it by hand. You can't just plug it into your calculator. Let's look at the scary looking one with all the trig functions in it. Number 38. Let's see, integral from 0 to pi over 3. I have sine of theta plus sine theta, tangent squared of theta, over secant squared of theta. Now I want you to pause this tape for a few minutes and think about how you would approach this. What'd you come up with? So when I first looked at it, I thought, maybe I'll write tangent as sine over cosine and secant as 1 over cosine. And I started that and it started getting uglier and messier. But while I was writing it, I realized that I have a sine here and a sine here. I can factor out a sine. 1 plus tangent squared of theta, all of that over secant squared of theta. And now Pythagorean identities are fresh in my mind. I have it written down right over here. Tangent squared plus 1 is secant squared. 1 plus tangent squared is the same as tangent squared plus 1. So actually this is sine of theta times secant squared of theta over secant squared of theta. That goes away. So I really just have integral from 0 to pi over 3 of sine, which is negative cosine from 0 to pi over 3. I plug in pi over 3 first, so that's negative cosine of pi over 3 minus negative cosine of 0. So negative cosine of pi over 3. Well, pi over 3 cosine is equal to 1/2. So negative 1/2 minus cosine of 0 is 1. So negative 1. And we end up with a half. A lot of work for a half. That one you could plug in your calculator and have it do the work for you.